Hi, this is Mr. Kieske. In my experience teaching pre-calculus and above, a lot of students have trouble with negative and fractional exponents, sometimes just exponents in general. So I decided to make this video to help out you guys who are struggling with exponents, especially negative and fractional exponents. So I want to take a few steps back and get to the nitty-gritty here so that you understand what exponentiation is really all about, and I want to distinguish it from something that you are familiar with. So I guess I just want to start with the concept of an identity. Okay, an identity has to be matched or paired with an operation. So an identity of addition and subtraction. First of all, addition and subtraction are really the same thing. Um, they're inverse operations, I suppose, but subtraction is just the addition of a negative number. Um, So the identity of addition and subtraction is 0 because when you add a number or subtract a number to 0 or with 0, you're going to end up with that same number. That's why it's called the identity. And the identity of multiplication and division is 1. If you add a number, if you multiply or divide a number by 1, you're going to end up with that same number. This is a really important facet to understand. I even want to take a further step back and understand that addition and multiplication are linked also. So if we start with the identity, if we start with the identity for addition, 0, and we add, say, 4 times, I would choose to start with 0 because it's the identity, it's the root of all, it's the beginning of all addition and subtraction. I'm going to get 16. And likewise, if I start with the identity for multiplication or division with it's 1, and I multiply 4 times, I'm going to get 4 to the 4th, which is 16 squared, which is 256. Okay, so what I've got going on here is sort of like I start with the identity, and I start with an identity, and then I do an operation with a number, and I would say maybe that so this is the 0th occurrence of the operation. This is the identity. This is the first. This is the second. This is the third, and this is the 4th repetition of that operation. Um, so to add one 4, it gets 4. To add a second 4 gives me 8. To add a third 4 gives me 12. To add a fourth 4 gives me 16. Starting with 1, to multiply 1 time, I get 4. To multiply 2 times, I get 16. To multiply 3 times, I get 64. And to multiply 4 times, I get 256. It's obvious when you look at multiplication and addition this way that you can see that multiplication is repeated addition. I mean, essentially, this is equal to 4 times 4. Okay, to repeat the addition of 4 times is 4 times 4, and what is repeated multiplication? Well, we call that exponentiation. So this is essentially 4 to the 4th. So to repeat multiplication, which actually is repeated multiplication, repeated addition. So repeated multiplication gives me exponentiation. So it's sort of like stacking these operations on top of each other. In fact, there is one more operation that is repeated exponentiation, people have various names for it. In fact, I'm not even going to write the name down. It's not really the point of this exercise, but there is such a thing as um, repeating multiple exponentiation like this. Um, and you can see that's going to grow very quickly. You have to work your way down. So this is the same as 4 to the 4 to the 16th, which is the same as 4 to the, I just did this on the calculator, 4 to 9, 4, 9, 6, 7 to 9, 6. I realize I'm going a little bit far afield here, but my point here in doing this is to show you that starting with 0, you as your identity for addition, you do repeated addition, and that produces a concept of multiplication. Starting with 1, the identity for multiplication, if you do repeated multiplication, you end up doing exponentiation. And I'm showing you that, in fact, you could continue to stack it up and say, well, let's repeat exponentiation 4 times, and you can see we get enormous numbers very quickly. Okay, so why did I do all this? Well, I'm just trying to distinguish addition and subtraction from multiplication and division. And then I'm trying to distinguish exponentiation and logarithms from addition, subtraction, and multiplication, division. So let's just go through the concept of inverses here. So addition and subtraction, they undo each other. Multiplication, and division, they undo each other. And then I would say exponentiation and logarithms, they undo each other. I think that by like 5th grade, you know, this one's cool and this one's cool. And it's like in 10th grade, when you got a whole lot of other stuff going on in school, this stuff tends to be a little unhappy. And students get hung up and they see an expression like the log base 2 of 8, and they write 4 because they haven't let their mind expand past division, when in fact this is 3, because you're asking what power of 2 gets me to 8, and it's 3. So what I'm asking you to think about in this problem is, you're starting with the identity 1. You're going to write a certain number of 2's until you repeat multiplication enough times to get to 8. How many times are you going to repeat that multiplication? 3 times. So you're counting. So this is sort of like in the same way I was talking about. This is the 0th repetition of multiplication by 2, because you start with 1. This is the first repetition. You're going to have 2. This is the second repetition. You're going to get to 4. And the third repetition is going to get us to 8. And so I'm asking you to think about counting differently. Okay, so let's try it. Let's count by 2's. You would go 2, 4, 6, 8, 10, 12, 14, 16. But what's interesting about that is I said count by 2's. Somebody really savvy would said, well, do you want to count by 2's with addition, or do you want to count by 2's with multiplication? And so when we say count by 2's, the implication is we're saying count by 2's with addition. We're just going to add 2, 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 and essentially we're working in the world of addition, starting obviously with 0 here. Now, if we counted by 2's with multiplication, we would go 2, 4, 8, 16, 32, 64, 128, 256. And you can see that we're multiplying now. Okay, so this is the world of counting by powers, and this is counting by I guess counting by addition. Okay, so I'm just trying to distinguish exponentials sorry, exponentiation from division, just to start us off. I hope that's clear. Okay, so now I can sort of ask the question, well, why is, you know, 8 to the 0 equal to 1? Let's make it a little easier. Let's make it, instead of 8 to the, let's just make it 3 to the 0 equal to 1. A lot of kids say, because my teacher told me. If you think about what's going on, this is saying, let's repeat multiplication by 3 0 times, and what do we get? And if you understand the concept of the identities, where do we start multiplication? Well, we start with 1, because if we started with 0 and repeated multiplication, 0 times 3 times 3 times 3 times 3, it's just going to leave us at 0. So we have to start 1 times 0 threes. That's going to equal 1. So it's a hard thing to write, but 0 threes, that's just going to equal 1. Okay. Another way of thinking about this is, and this is going to help me understand negative exponents, but let's just say we were working with 3 to the 4th, which is 3 times 3 times 3 times 3, which is 81. 3 cubed is 3 times 3 times 3, which is 27. 3 squared is 3 times 3, which is equal to 9. 3 to the first power is just 3. And you can see every step down I take here, I'm essentially dividing by 3. And so it makes sense that the next iteration of this, 3 to the 0, would be, let me just keep dividing by 1, sorry, dividing by 3, and you can see I'm going to get 1 here. And you can see what's missing in every single one of these expressions is the identity. 1 times, 1 times, 1 times, and all you're left with is 1. Okay, so it's really 1 times a certain number of 3's when you do exponentiation. Just like when you're doing addition or multiplication, I say 6 times 4. Okay, I'm going to start with 0 4's, and I'm going to add 4 6 times, and I'm going to get to 24. Okay, now the negative exponent comes rather simply if you go from here. 3 to the negative first power? Well, if I multiply by a 3 negative 1 times, that's a tough thing to think about. Maybe what I should think about is, let me just continue to divide by 3, and I see that I'm going to get 1/3 here. Oh, I see. Maybe multiplying by 3 negative 1 times is the same as dividing by 3. So it's like 1 divided by 3. And if I do 3 to the negative 2 power, I start with 1, I divide by 3, and I divide by 3 again, and I'm going to get 1/9. Because 1/3 of 1/3 is 1/9. Okay, and so you can think about, in this respect, if I continue to do this, 3 to the negative, say, n times, I'm going to do 1 divided by 3 divided by 3 divided by 3 onwards and onwards, and I'm going to have n repetitions of that. This is going to equal 1 over 3 to the nth power. And you can see now that this is something that you might have memorized. But now I hope that you have replaced that memorization with this understanding of what a negative exponent really indicates, and that is repeated inverse multiplication. So that's the point of that. While we're here, let's think about something like 6 to the 3rd times 4 to the negative 2 over 5 squared times 2 to the negative 5th. Okay, now what I'm going to say is that instead of making reciprocals out of 4 to the negative 2 and 2 to the negative fifth and dealing with a complex fraction, for example, I could write this as in this way. I don't think that helps me. It is the sort of direct result of the rule I just created above. But I don't like this because it creates an ugly fraction inside of a fraction. So I'm going to eliminate that. And what I'm going to say is 4 to the negative 2 is saying, because of the order of operations here, which enables me to do any multiplication division in any order I want, I can say that 6 to the third over 5 squared, I can write this as times 4 to the negative 2 times 1 over 2 to the negative fifth. Okay? And then I can write this as 6 to the third over 5 squared times 1 over 4 squared times the reciprocal of 2 to the negative fifth is just 2 to the fifth over 1. Okay? And that this is now going to be 6 to the third times 2 to the fifth over 5 squared times 4 squared. And then I would suggest that you look at this and you skip right down to this. I would not suggest doing this whole process each time. I would say that once you understand that the negative exponent is really just asking you to think about a reciprocal, I would say, look at this. 6 to the third stayed where it was. 4 to the negative 2 became 4 to the 2 in the denominator. 5 squared stays where it was. 2 to the negative fifth became 2 to the positive fifth in the numerator. So essentially what you're doing with negative exponents is taking a reciprocal, which is the same thing as saying, well, if it's multiplying now, to do its reciprocal is to divide it later. And to divide it now is to do its multiplication later. That's as best as I can explain that. Okay, so what about fractional exponents? Okay, back to this idea of counting by powers. Let's work with base 3. Scratch that. Let's work with base 4. Let's do 4 to the 3 halves power. Okay. You might have memorized something about this, or had your teacher shown you that this was maybe the same thing as 4 to the 1/2 cubed, which is also equal to 4 cubed to the 1/2. And the exponent rules allow you to rearrange those exponents whatever way you want. And you know that this is going to equal, in both cases, I think you get 8. 8 is both 4 to the 1/2 cubed and 4 cubed to the 1/2. But I'm only doing that because I want to show that the number is 8 by way of a memorized process you might have encountered before. But I want to get to 8 intuitively. Let's count by powers of 4. 1 is the 0th power of 4. 4 is the next power of 4. 16 is the next power of 4. And then 64 is the next power of 4. I don't know why I'm putting multiplication signs in here. And then the next one is 256. So this is the 0th, the 1st, the 2nd, the 3rd, the 4th. Okay. And I'm asking for the 3/2 power, which is really 4 to the 1/2. So the number is certainly going to be between 4 to the 1 and 4 to the 2. It's going to be somewhere in here. And it's going to be halfway between 4 and 16. And I say halfway very carefully because you might think of halfway between 4 and 16 as the middle number between 4 and 16, which is 10. But it's not halfway by addition. It's halfway by multiplication. So instead of, I'm asking for what number is halfway between 4 and 16 by multiplication. So I want to go 4 to something to 16, by multiplication. So I'm going to multiply by a number here times something, and I'm going to multiply again, repeated multiplication to get here. And you can see that the number I'm going to multiply by twice to get to 16 is 2. So 4 times 2 is 8, and then 8 times 2 is 16. And so you can see that now 8 is really the middle number between 4 and 16 if you're counting by powers. Let's try a different example. Let's use base 9. Let's go 9. Sorry, 1 is the first, is the 0th power of 9, and then 81 is the next one, and then 729 is the one after that. And again, I want to do 9 to the 3 halves power. Intuitively, that is going to be between, so sorry, this is 9 to the 0, this is 9 to the 1, this is 9 squared, this is 9 cubed. So 9 to the 3 halves power, again, 9 to the 1 and a half, is going to be somewhere in here. So 9 to the 1 and a half, I have to get from 9 to 81. 9 to 81. There's a number in the middle here that when I multiply repeatedly times something again, I'm going to get a number in the middle. So what do I multiply twice to get to 81? I multiply by 3 twice. So times 3, and that's going to get me 27. So 9 to the 3 halves power is 27, intuitively. To go back to our exponent rules, we could say 9 to the 3 halves is equal to 9 to the 1 half cubed, which is equal to 9 cubed to the 1 half. It's much easier to evaluate this one here. That's 3 cubed, which is 27. This is 9 cubed, 729 to the 1 half, which is the square root, and that's also 27. Yet another way to think about, intuitive way to think about fractional exponents is that, let's say you've got this expression 64 to the 1 half power. Okay, I know that you know what your exponent rules. I hope you know a bit about them. I hope you know that 64 to the 1 half power times 64 to the 1 half power is equal to 64 to the 1 half plus 1 half. When you multiply expressions of the same base, you add their exponents, and you get 64 to the 1, which equals 64. So if you look carefully at this, we're saying that 64 to the 1 half times 64 to the 1 half equals 64. Multiplying this number by itself gives me 64. Oh, this must be the square root of 64, because the square root of 64 is the number that you multiply by itself to get 64. Oh, the square root of 64 is 8. So therefore, 64 to the 1 half power is equal to the square root of 64, which equals 8. How about 64 to the 1/3 power? Well, 64 to the 1/3 times 64 to the 1/3 times 64 to the 1/3 is going to be 64 to the 1/3 plus 1/3 plus 1/3, which equals 64 to the 1, which equals 64. So we're saying that 64 to the 1/3 times itself again gets me to 64. The number that you multiply by itself 3 times to get to 64, that's the cube root of 64. That has to equal 64. So the cube root is 64. Well, what number times itself 3 times gives me 64? That number is 4. Okay, so now we've got 64 to the 1/3 is equal to the cube root of 64, which equals 4. So I think we can generalize now, and we can say that, okay, some number b raised to the 1 over nth power is going to be the nth root of b. And finally, let's just summarize a little bit here. When we say the square root of 64, we're really saying, how do I get from 1 to 64 multiplying once by the same thing, or multiplying twice by the same thing? And you can see that I have to multiply by 8, and multiply by 8 again, I have to get to 8. And when I say what's the cube root, I'm going to have to multiply 3 times by something, times something here, times something here, and times something here again to 64. And you can see I'm going to multiply by 4 times 4 here is going to give me 16 times 4 there. So essentially, again, we're counting by powers. We're jumping by powers instead of jumping by addition. And that takes me back to my original discussion here of why we talked about repeated addition and repeated multiplication. So I hope that makes sense. I know that I didn't talk much about logarithms here, but to do a logarithm is just to count how many powers. And if you start thinking logarithms in those terms, I think you'll have much better success. Hope that's clear.